I would like to start by first thanking the organizers for the opportunity to present this work here. So I'll talk about supersymmetry beyond flat space, and this work is based in collaboration with Cyril Closet from the Weizmann Institute, Thomas Dumitrescu and Guido Festocia from the Institute for Advanced Study, and Itamar Shamir also from the Weizmann Institute. So, and we hope it will appear soon. Right, so supersymmetry in flat space, as we've all seen in the last couple of decades, leads to many interesting and stringent constraints on the dynamics of strongly coupled gauge theories. The most powerful methods in analyzing supersymmetric gauge theories over the years have been general consistency conditions of quantum field theories, such as anomalies, and most powerful were the constraints coming from holomorphy, from chiral operators, and the chiral ring. But in recent years, we've learned that there might be much more to learn about supersymmetry beyond the sector of chiral ring and so on. For example, recently people have been computing partition functions on various curved spaces, most notably S3 times S1, and these computations probe something beyond the sector of chiral operators. These computations are in some sense sensitive to operators that are annihilated by one supercharge rather than by two supercharges. Similarly, in three-dimensional field theories on three spheres, the analysis has also led to many new exact results about the dynamics of quantum field theory, including various lessons that we've learned about renormalization group flows, entanglement entropy, and many other aspects of three-dimensional field theories that have not been accessible before. So our motivation in this project is to study four supercharges theories compactified on various curved manifolds. And the idea is to somehow generalize what has been done so far in order to understand better the results that have already been achieved and to extend them further. So the motivations are, of course, to derive new constraints, understand better strongly coupled dynamics in flat space. And we've already seen that some of the tools that we get by doing that are beyond what is immediately available in flat space. Also, a more mathematical motivation is that studying in general what does it mean to compactify four supercharges theories on curved manifolds can lead to some new mathematical questions or mathematical ideas which would somehow be the analog of what we know about n equals 2 theories on curved spaces. In particular, one could ask what is the four supercharges analog of Donaldson theories and questions of this kind. Also, there are many curious properties that people have found by essentially trial and error or by looking at the answer of partition functions on S3 and S3 times S1 and various others. And these properties go under the names of holomorphy. There is a decomposition into blocks. We'll hear about these things probably in the next lectures. There is some SL3Z mysterious symmetry or mysterious action on partition functions and many others. So it's very likely that to understand where this come from, you need to extend what is currently known into some general framework, and then to deform what is currently known into some general framework. And then somehow this would be consequences of some general properties of partition functions. So the main goal in this talk is to understand four-dimensional n equals 1 theories on four manifolds, and similarly n equals 2 theories on three manifolds. They all have four supercharges. So the first thing one should note is that when you want to compactify quantum field theory in some curved manifold, it's not unique. So first of all, you can always add couplings to curvature. So that's ambiguity number one. And additionally, if you turn on a non-trivial metric, you could also naturally turn on various other background fields, not just the metric, but additional gauge fields or various additional background fields. So there is a systematic way to think about all these things, starting from flat space. So let's consider n equals 1 in 4 dimensions, and let's further assume that there is an R symmetry. So the energy momentum tensor sits in some n equals 1 multiplet, which contains the R current, the energy momentum tensor, and some closed 2 form. So you might have thought that the multiplet just contains the R symmetry and the energy momentum tensor, but in fact, you must add this closed 2 form for the multiplet to be consistent. So this is a 12 plus 12 multiplet, and if we start from this multiplet, we can imagine coupling this multiplet to various background fields. And that would be the correct notion of coupling a supersymmetric theory to curved space. So you not only couple the energy momentum tensor to a metric, you also allow coupling the R current to some background gauge field, and this 2 form is coupled to some Kalb-Ramond field, a 2 form gauge field. So these fields are not pass integrated over, they are frozen. They're just fixed background fields. And if you choose these background fields to be whatever, some random choice, you would not have any preserved supersymmetry. Only very special choices of these background fields preserve some leftover supersymmetry. It turns out that if all you want is to preserve one supersymmetry on a curved manifold, then there is a very simple, sufficient, and necessary condition, which is that the manifold admits a complex structure and a Hermitian metric. So if you have a Hermitian manifold, a manifold with a which is complex and also the metric respects Hermitian structure, then there is one leftover supersymmetry, at least one leftover supersymmetry, and the algebra that this supersymmetry satisfies is that it's nilpotent. So that's the most general condition kinematically for there to exist at least one supersymmetry on a curved space. Another curious case that I want to note is that if the manifold looks locally like a torus times some two-dimensional space, then in fact you can preserve two supercharges, and the algebra is somewhat more complicated than this. From this point of view, the familiar case that's been studied in the literature very extensively, S3 times S1, is just a fibration of a torus over a Riemann surface, whereby you decompose the sphere as an S1 fibration of S2, and the whole fiber is joined with this S1 to view it as a torus fibration over S2. This particular fibration, in fact, preserves 4 supercharges, and that's the only fibration of this type that preserves 4 supercharges. Now, imagine that the theory also has a global symmetry. So a global symmetry in supersymmetry is embedded into some multiplet. The bosonic components in this multiplet include the current, which is conserved, and some scalar operator J. And it's natural to also couple these guys to some background fields. Let's denote the background field to which the current is coupled by A mu, and the background field to which the scalar is coupled by D. Again, if you turn on general expectation values for A mu and D, you would break supersymmetry completely. It turns out that a necessary and sufficient condition for there to exist at least one leftover supersymmetry is that the corresponding G bundle is holomorphic. So the conclusion from this kinematical analysis, so far there was no essential dynamics, it's just kinematics. There is a leftover supersymmetry if you couple the theory to curved space and you allow the global symmetries to couple to some background fields, if and only if the manifold is complex and the global symmetry bundle is holomorphic. So that's the data that must exist if you want to preserve at least one supersymmetry. And of course, all the examples that people have studied in the literature in 4 dimensions are consistent with this criterion. Now, the main question that we're after in this talk is that suppose you specify for a manifold. It could be S3 times S1, if you want to have an example in mind, which is complex, and it has a Hermitian metric. If there are some global symmetries in the theory, you can additionally add background fields for these global symmetries, as long as they comprise a holomorphic G bundle, as I mentioned. So the first main question that I want to discuss is that we have this partition function, which is now a function of the complex structure, the Hermitian metric, the G bundle, and many other parameters, including parameters that appear in the Lagrangian itself. So the first question that we've investigated is what does this depend on? Of course, if it were a non-supersymmetric theory, it would depend on in a very complicated way on the metric and all the other data. But since there is supersymmetry, even one supersymmetry, you might expect that this is a very special function. It does not depend on all the data in this theory. So let me quote the results. These are the main results of this question. So given the complex structure, it turns out that the partition function is completely independent of the metric. This is a very useful fact. It can be essentially used to replace what people call localization. You just take the manifold to be very small, in a sense. And it can also be used to prove to argue for various other things that people have found by trial and error, essentially. So now we know that the partition function is completely independent of the Hermitian metric. The dependence on the complex structure is there, but it takes a very special form. It depends only holomorphically on the complex structure moduli. So if you think about a torus in 2 dimensions, there is tau and tau bar. The partition function is a holomorphic function of tau. To be more precise, it's a meromorphic function of tau. There are various poles in the complex structure moduli space that appear if you compute some examples. Additionally, if there are global symmetries, it turns out that the partition function depends holomorphically on the moduli that parameterize these G bundles. So it turns out that the partition function of n equals 1 theories, which in contradistinction to n equals 2 theories, is not topological. It computes invariance of complex structure in 4 dimensions, and also invariance of the complex structure of global symmetry bundles. That's in contradistinction to n equals 2 theories, where the answer is topological in some way. So let's consider some applications and examples. One example is S3 times S1, which is a nice complex manifold. It's not scalar. And this manifold was studied by Kodaira and Spencer long ago. They found that the moduli space of complex structures is 2 complex dimensional. So like the torus in 2 dimensions has a one-dimensional moduli space of complex structures. This space has a two complex dimensional space of complex structures, which Kodara and Spencer denote by S and T. On the other hand, when physicists computed the partition function over S3 times S1, they found it convenient to add various chemical potentials on the S1. And they found two parameters, P and Q, that are related to chemical potentials on the S1. Indeed, from our result, it follows that there is a one-to-one map between S and T and P and Q. So the partition function, which in the literature is written as a function of various chemical potentials, and it has very many interesting properties, should really be interpreted as a function on the moduli space of complex structures of S3 times S1. And you can establish the correspondence between S and T and P and Q very explicitly. There is a formula that relates P and Q to the complex structure moduli space of S3 times S1. And of course, there is a similar story for any other complex manifold, for length spaces, and so on. If you have a U1 global symmetry, then physicists, of course, computing these partition functions, found it convenient to add a chemical potential for this global symmetry. And this corresponds to some holomorphic U1 bundle over S3 times S1, which is also very well understood mathematically. So this is the proper interpretation of the partition function on S3 times S1. It's just a function of the moduli space of complex structures of S3 times S1. Now, if the manifold is of the type T2 times a Riemann surface, at least locally, you can say a bit more. So to make it short, it turns out that the dependence on the complex structure is even more special than what I said previously. It depends holomorphically just on some of the components of the complex structure, not on all of the components of the complex structure. In particular, the answer does not depend on the complex structure of sigma. It depends only on the complex structure of the torus and some complex structure which arises from the fact that there is a product. But it does not depend on the inherent complex structure moduli of sigma. So the partition function is even more special in this general case. Now, let me tell you what happens in three-dimensional theories. So we ask essentially the same question for three-dimensional theories, starting from theories with four supercharges on three-dimensional spaces within R symmetry. And one can ask which three manifolds are consistent with at least one leftover supersymmetry. That's a very general question. And we know one answer already, it's S3, because people computed the partition function in S3 in many examples, for many field theories and so on. What we found is a certain mathematical structure which guarantees it's a necessary and sufficient condition for there to exist at least one supersymmetry on a S3 manifold. So let me just walk you through this structure quickly. So we call this structure an integrable almost contact structure. As I'll mention in the next few slides, mathematicians have not discovered this structure, even though it appears as naturally as complex structure in 4 dimensions. But basically, the manifold is required to have a vector, a form, and a certain map of the tangent space to itself, which satisfies some funny identities. And there is an integrability condition, which is very crucial. So this integrability condition was not studied in the mathematical literature. We did some analysis of what this integrability condition implies, and it turns out that if you impose this integrability condition on 3 manifolds, you find properties which are tantalizingly similar to complex geometry in 4 dimensions. In particular, these 3 manifolds with this integrability condition, they have an analog of Dolbeault homology, even though it's odd dimensional, and they have an analog of Kodara-Spencer theory, meaning there is a moduli space of these structures, and this moduli space looks very similar to the moduli space in 4-dimensional manifolds. For example, we analyzed basic aspects of this moduli space for the sphere sphere, for the topological sphere sphere. On the other hand, we do not have a good understanding of which 3 manifolds admit this structure. We know for sure a big class of manifolds such as Seifert manifolds where this structure exists, but we don't know in general which manifolds admit this structure, whether there is an obstruction or not. Now, we proved that the supersymmetric partition function on 3 manifolds does not know anything about the metric, again. It's only sensitive to this integrable almost contact structure. So, since we proved that on manifolds that are topologically S3, there is only a 1-dimensional space of integrable almost contact structure. And this is in 1-to-1 correspondence with what people call the squashing parameter in the literature. So this squashing parameter that appears in HHL, Hamahosomichili, for example, is in 1-to-1 correspondence with this moduli space of various contact structures, integrable almost contact structures that you can put in a sphere sphere. And this has several consequences. For example, one immediate corollary of these results is that there will never be new partition functions beyond the one of Hama-Hosomichi and Lee. And many of the experts in the audience know that people have constructed many, many different squashings of the sphere sphere, and they were sometimes surprised to find the same results as for the squashing of Hama-Hosomichi Lee. But this is now, we understand why this happens. It's because the moduli space of integrable almost contact structures is 1-dimensional, so there cannot be anything new. Actually, in the original paper of HHL, they found two types of squashing, and they were surprised that one of them is trivial. It did not lead to interesting results. And that's because the integrable almost contact structure in the other, in this squashing is trivial. It's the same as that of the round S3. Also, Imamura, for example, constructed various interesting squashings, and he found the same results as HHL. And more recently, there were papers by Martelli and Pasillas, where they couldn't, I think, at this point, carry out localization completely, but they did some holographic computations, and their computations are not inconsistent with this claim, that in the end they'll find the same answer as before. So one additional application is that the dependence on this integrable almost contact structure can lead to various results about flat space, quantum field theory. This was pursued, for example, in this paper, and it can lead to exact computations of various non-chiral quantities in three-dimensional N equals 2 theories. We don't know if these particular results can be derived from flat space directly. One could get a non-perturbative formula in flat space directly. So even though this mathematical structure in 3 dimensions seems a bit unfamiliar, it has very similar properties to 4-dimensional complex structures, and it arises physically as naturally as complex structure in 4 dimensions. So one would think that this is a natural structure that mathematicians should investigate in 3 dimensions. Let me briefly conclude what I've said so far. So we use the tools of generating functionals, studying the partition function as a function of various parameters that appear in the theory. And we studied the dependence of this partition function on various quantities, such as the complex structure, the metric, and so on. We proved that for 4-dimensional N equals 1 theories, the partition function computes invariance of the complex structure, and that has many consequences, out of which I listed very few. In 3 dimensions, the partition function computes invariance of the integrable almost contact structure. It's again independent of the metric, and I listed some very few consequences of this too. Well, in particular, the consequences that I listed were that there is an interpretation of the parameters appearing in the partition function over S3 times S1 in the form of the complex structure moduli space of S3 times S1. And similarly, we explained why various squashings that people have discussed in the literature that were so far maybe mysterious gave the same result as the original squashing of Hama, Hosamichi, and Lee. That follows very easily from these results. So some of the outstanding open questions is which additional conditions can be imposed on this manifold such that the answer is in fact topological. It does not even depend on the complex structure. One particular condition that we know leads to a topological answer is that the 4 manifold is the Calabi-Yau. Then the answer is in fact topological. But that, of course, there are very few manifolds of this type in 4 dimensions, and we don't know whether this is an exhaustive answer. Another interesting comment is that the partition functions, if you view them as functions of the moduli space of complex structures, you compute simple examples such as free chiral fields, you find that there are poles, simple poles, in the space of complex structure moduli. It's an outstanding question to understand what is the meaning of these poles. Another question which is mathematical in nature is to understand whether there is any obstruction to having this integrable almost contact structure on a 3 manifold, on a generic 3 manifold. Of course, the hope of this program, one of the hopes of this program is that since we've now shown that the function is just a moromorphic function of the complex structure moduli space, if one could understand where the poles are and what fixes the location of these poles and their coefficients, one could reconstruct the whole function, and one would never need to do any computation explicitly. So by using Spurian analysis or holomorphy, if you want, one could hope that one could reproduce the full partition function on any complex 4 manifold. The generalization to 6 dimensions, 5 dimensions, and N equals 2 theories in 4 dimensions is also an obvious open question. Let me mention the relation to twisting. One might be confused of how does this relate to the fact that there is no naive twisting that you can do for N equals 1 theories in flat space. So the way it works is as follows. You start from flat space. Let's start for simplicity from R4. And let's choose a preferred spinor, 0, 1. If you choose a preferred spinor in 4 dimensions, it defines a complex structure on R4. So it defines what you call complex coordinates on flat space. The way you go from a spinor to complex structure is just by looking at this bilinear. Now, holomorphic coordinate transformations are U2 transformations on the frame, on some holomorphic adapted frame. Since this is a U2 which is embedded in SU2 times SU2, which is the structure group in 4 dimensions, there is a U1 which can be twisted away by the R symmetry. So if your theory has an R symmetry, and if you only allow yourself to use holomorphic coordinate transformations, you get a scalar supercharge. Indeed, this particular spinor becomes a scalar under complex coordinate transformations. I should know that it's not a scalar under general coordinate transformations. It's only a scalar under holomorphic coordinate transformations. And in this sense, we have a scalar supercharge that allows us to couple the theory to an arbitrary complex manifold. But note that the theory that we get is not topological. It computes invariance of the complex structure. Now, let me briefly also outline how these results that I mentioned are derived. So the main question that one should ask oneself is, what is the cohomology in flat space of these operators that appear in the 12 plus 12 multiplet in flat space? So the multiplet consists of the R symmetry, the energy momentum tensor, and a certain closed two form. And let's pick a spinor of the type 0, 1. A very concrete question that one could analyze is which operators are delta closed and which of them are delta exact. So some linear combinations of these operators would be delta closed, and some linear combinations would be delta exact, and also in particular delta closed. It turns out that all the delta closed operators are in fact delta exact, and they fall into two categories. They have an energy momentum tensor with barred indices, or one unbarred index and one barred index. This immediately means that deformations of the theory that are sensitive to two bar indices, or one unbarred index and one barred index, do not influence the partition function, at least at the linear level. And that immediately means that the answer depends holomorphically on the complex structure moduli space. This is at the level of linearized analysis. One can then extend this analysis to the full nonlinear level, or to show that this linear analysis is sufficient, but I won't go into that. Let me just go back to the conclusions, and I'll stop here.
Okay, questions or comments?
So I just wanted to make sure, I think it's implicit in your talk, but you really meant complex structure in 4 dimensions, not almost complex structure.
It must satisfy the integrability condition.
Okay, and the manifolds are compact? Are you assuming that, or is it important?
Yeah, we're assuming that in order for the partition function to be well-defined.
Well, you could have non-compact manifold with boundary conditions and make a well-defined.
Yeah. Another generalization of this study that I have not mentioned, but I should have maybe, is that one could study manifolds with boundary.
Right.
This is something that some of us are pursuing, but I've not mentioned that here explicitly.
And finally, you mentioned independence of the metric.
Yes.
Well, even in the Donaldson-Witten example in 4-dimension n equals 2, when the manifold has B2 plus equals 1, in fact, there's wall crossing and there is some metric dependence. And I was wondering, is there room for that kind of phenomenon
Yeah,
here?
so when I said that it's independent of the metric, this is barring anomalies. So various anomalies could perhaps introduce
Right, so you could get
a
a total derivative in field space which doesn't vanish as you change. So as I assume that as you change, how do you prove that it's independent of the metric?
You can prove that up to if there are no anomalies in various changes of variables, then the theory must be independent of the metric.
Right, so does that involve a total derivative in field space?
Yeah, it could come, the metric dependence could come in the form of some anomaly, but I think in this case it would be very constrained and not, it won't be a genuine part of the answer. It will be fixed by anomalies.
Any other? Ed?
I'm curious about the meaning of the statement that on S3 there's just a one-parameter family of those almost integrable, almost contact structures. Is what you mean actually that the standard one only has a single deformation, one-parameter family of deformations? Or, in other words, could there be one that isn't continuously connected to the standard one?
Yes. So I can answer this question quite satisfactorily. So as you know, in 4 dimensions, there is a linearized analysis of which complex structure deformations can exist. And sometimes there is a nonlinear obstruction. So not every linear deformation can be extended to a full-fledged deformation of the complex structure. So in 3 dimensions, the same phenomena could exist. We checked it. And for S3, the set of large deformations of the integrable almost contact structure that we found is indeed one complex dimensional. But that's just a connected patch of the full moduli space that starts from the round sphere. There are disconnected components. I think maybe it would take me more time than I have, but I could tell you in private. We characterize them quite meticulously. Yes, but I should note, I want to know that this one-dimensional space of deformations preserves two supercharges, while the additional ones that are disconnected preserve just one supercharge. Nobody has ever managed to compute the partition functions corresponding to those.
Sergey.
So there are different types of partition functions. Some can be interpreted in radial quantization as indices, and they have integer coefficients, and others, like sphere partition functions, they have just random coefficients. So from the viewpoint of moduli of complex structure, is there a simple criterion which will allow me to tell a priori which ones will be indices and which ones will be not?
I think maybe I'll rephrase your question in a way that I want to understand it, but maybe you should tell me if that's the correct rephrasal. So you're asking if these partition functions have a clear meaning of computing something in flat space. Is that the question? So in some special cases, like S3 times S1, if you compute the partition function on S3 times S1 for a conformal field theory, then it has the interpretation of computing some partition of of special representations of the superconformal group in flat space. That's a paper of Minwala, Maldacena, and Raju and several other authors. But in most cases, nobody knows what's the interpretation of these partition functions in terms of flat space. We did some work a year ago with these authors, where we found some snippets of this, some bits and pieces of this partition function, of the full-fledged partition functions, have a clear interpretation in flat space. But I think it's fair to say that we don't know what's the general content of this partition function phrased in terms of flat space quantities.
Any other? Okay, if not, let's thank the speaker again.